Welcome to welcome to the European Non-Associative Algebra Seminar. Today's speaker is Seidon Alsaody from Uppsala University, Sweden. He's going to talk about Brown algebras, Freudenthal's triple systems, and exceptional groups over rings. Please.
Thank you very much, and thank you for the invitation. I'm very happy to be here, and I'm honored to be speaking at this seminar, and very happy that the seminar exists. I will exactly be talking about Brown algebras, Freudenthal triple systems, and exceptional groups of rings. Please interrupt me if I'm heard poorly or if you have any questions. So this is work that I'm happy to say, is on arXiv, and I will start by giving some background to the whole business. So what is our goal? Our goal is to understand exceptional non-associative algebras, and together with them, exceptional groups over rings. So most of these objects are well understood over fields, at least if the characteristic is nice enough. And we want to understand them over rings because of applications in number theory and geometry. And for example, in theoretical physics, they study G2 manifolds. So these are octonion algebras over rings and so on. So let me start section 0 by giving some examples over what I mean by understand and what algebras we want to deal with. So let's start by taking C, an octonion algebra. So you saw, of course, this being a seminar on non-associative algebras, octonion algebras are the non-associative algebras par excellence. So I shouldn't say too much about what these are. And also in the last talk by Alberto El Duque, you encountered those in the framework of composition algebras. They are algebras of, if you're over a field dimension 8, with a quadratic form Q that has some nice properties. And so how do the groups come in? Well, the automorphism group of C is a group of type G2, so that's an exceptional algebraic group. And I'm being vague now whether we're working over fields or rings. This applies over rings, but you can think of it over fields this far. Then if you look at the orthogonal group of the quadratic form, take its connected component and take the sort of simply connected cover of this, you get the spin group of Q. And this is a group of type D4, which for the purposes of this talk is an exceptional group because of its Dynkin diagram, which is the only one that has an order 3 automorphism, and that gives us triality. And triality is at the core of a map you can get from spin Q to 2 copies of the unit sphere. So the unit sphere, this is the set of all x in C such that Q of x is equal to 1. If you view these algebraic geometrically as schemes, you can see this as a homogeneous space. So spin Q is a homogeneous space over SQ squared, and the structure group is the automorphism group of the octonion algebra. This means that over every point of this space here, you have a fiber that is some twist of this automorphism group. And so using algebraic geometry, you can think of this, I mean, as a G2 torsor. So I'll go into details later, but the point so far is that this is something you can twist the algebra C with. So twisting and C by this torsor gives all isotopes of C. This was a result, joint work with Philippe Gilles in 2019. And what are these isotopes? Well, these are the algebras CAB, where the multiplication xy being XA BY, where A and B are elements of this unit sphere. So if you twist by the fiber of AB, you get another octonion algebra, and that is precisely the isotope. And this way, you can say, so the isotopes have been known since the 40s, but with this machinery, you can say when isotopes are isomorphic or not, and in fact deduce that there are octonion algebras that have non-isomorphic isotopes. So this example started the whole business of doing this with other more complicated non-associative algebras and their corresponding groups. So the next example is if you take an Albert algebra. This is an exceptional Jordan algebra. And there you can play almost the same game because you have n, its cubic form. And so the automorphism group of A is of type F4. The isometry group of n is of type E6. So here you get E6 as a homogeneous space over some version of a sphere. And you can play the same game and deduce that the twists by this homogeneous space, they are precisely corresponding to the isotopes of the Albert algebra, which is a known concept for Albert algebras. So to sort of conclude this informal introduction, what are we doing here? So we started with the octonion algebras. I could start with D4, groups of type D4, viewing them as torsors or homogeneous spaces under simpler groups over some concrete variety. Okay, so now, and also in the second step, I could understand groups of type E6 over some other variety as fibrations with structure group of type F4. There is an intermediate step where I can view F4 as a D4 a homogeneous space over some variety here. And the point is that each time I am so D4 goes into here, and then F4 goes into here. So each time I understand some group, I can use this machinery using a more complicated non-associative algebra to get a bigger fibration. And so in the next step, the natural thing is to try to consider E7 as a fibration whose fibers are essentially groups of type E6 over some variety here. And in order to do this, we need Brown algebras. and Freudenthal triple systems. These ingredients will give us this vibration and will help us understand isotopes of Brown algebras. So this is the pink step, is the step I'm going to talk about today. And maybe I can ask if there are any remarks so far. Okay, so let's start with a bit more precise stuff. So I'm working over a unital commutative ring R at some either 2 or 3 or both to be invertible, but in general, there is no further requirement on the ring R. So first, what the ingredients to need. So we want to define Brown algebras and their corresponding Freudenthal triple systems. So we need, for starters, Albert algebras. So an Albert algebra A over R is a cubic Jordan algebra. I will explain a bit what cubic means. And so it's a module with some Jordan multiplication or Jordan operation, whose underlying module is projective of constant rank 27, and such that if I tensor this algebra with a field over R, I get a simple Jordan algebra. Okay. So what does cubic Jordan algebra mean? It means I have a cubic form N. I have a quadratic adjoint. So N goes from A to R. So I have some extra structure, quadratic adjoint from A to A. And this gives me a trace map T from A times A to R, and also a cross product. So the trace map comes from linearizing the norm. The cross product is given by A cross B. This is the linearization of the quadratic adjoint. So it has all these structures. These maps satisfy certain compatibility conditions, and with the help of those, one defines the multiplication or whatever one defines on this to get the Jordan algebra. This might seem a bit tedious. There is another way to define Albert algebras by saying that A is locally, with respect to the FPPF topology, I will explain what that means, isomorphic to H3C, the algebra of 3 times 3 matrices that are Hermitian over an octonion algebra C. So what this means, FPPF locally isomorphic, and this is a theme that will be sort of coming back often, is that if I take A and the 3 times 3 Hermitian matrix over C, these might not be isomorphic necessarily, but I can tensor with some ring S over R and get isomorphism when I tensor over R. And S should be faithfully flat over R, which is basically a nice ring extension, an extension that respects the properties of exact sequences. So this is what we need to know. Okay, so Albert algebras are these exceptional, excuse me, Jordan algebras. And now we want to do something with them. We want to construct our Brown algebras. So what is a Brown algebra? Well, let's start with the reduced Brown algebra. So take A, an Albert algebra, over R. The reduced Brown algebra BA associated to A is the R algebra. So R module with multiplication. So I denote this BA, and it's just two copies of the ring itself and 2 copies of the Albert algebra that I write as a matrix in this way. And this is an algebra, so it has a multiplication. The multiplication is RABS times R prime, A prime, B prime, S prime is given by some formula using the trace of the Albert algebra the cross product of the Albert algebra and that's it. And it's not just an algebra, it has an involution star given by permuting the scalars. So where does this come from? Well, it's sort of an analog of the Cayley-Dixon construction of going from a quaternion algebra to an octonion algebra. This should remind a little of this. So this is a reduced Brown algebra associated to a given Albert algebra. And because we want to use algebraic geometry and want to look at things that are locally isomorphic, we give the name Brown algebra to any algebra with involution that becomes locally isomorphic to a reduced Brown algebra, meaning after a faithfully flat extension, it becomes like this. So a Brown algebra is an algebra with involution B such that B times S over R is isomorphic to this BA times S over R for some A Albert algebra and S over R faithfully flat. So, in some sense, locally isomorphic. So these Brown algebras are algebras in their own right, but we will use them in the context of Freudenthal triple systems. So what we now have is some sort of algebra. Algebra with involution. I forgot to add the requirement that I want the underlying module to be projective of constant rank 56, generalizing the fact that over fields this is a 56-dimensional algebra. So that is Brown algebras. Now the next step is to define Freudenthal triple systems. So what are Freudenthal triple systems? That's a general notion. And what I will work with today will, for some of you, probably be a special case of Freudenthal triple systems. So we'll see. So what you do is you start with a reduced Brown algebra. So Brown algebras were studied already by Brown back in the 60s already. And so they are quite an old object of study. So Brown algebra BA. And on that, you define a bilinear form. B that sends the pair R A B S, comma R prime A prime B prime S prime to R S prime minus R prime S plus T A B prime minus T A prime B. So this is alternating non-degenerate. And then you define a quartic form Q from A to R. And then what do you do? So classically, if 6 is invertible, so classically, these objects, including Brown algebras, were only studied under the assumption that 6 is invertible. So if you're over a field, characteristic is different from 2 and 3. So if 6 is invertible, then you can define a trilinear form as follows. So you want to define a trilinear form. And what do I want to call the trilinear form? Maybe T in the following way. So T of X, Y, Z. Well, since your bilinear form is non-degenerate, it's enough to know what this does under the bilinear form, and you require that this is the linearization of Q. So W, X, Y, Z. And then you call BA under this bilinear form and this trilinear form a sort of reduced Freudenthal triple system, let's say, reduced FTS. Now, this year there was actually a breakthrough in this world due to a paper by Garibaldi, Peterson, and Racine. I mean, okay, I guess we're in 2023 now. So last year there was a breakthrough, and they could do away with the requirement that 6 is invertible by replacing this T by a 4 linear form, replacing T and Q, the quartic form, by a 4 linear form psi. So you get BA, B, psi. And so I agree with them that this is the right way to view Freudenthal triple systems. In the case when 6 is invertible, you can get exactly this data from this psi. So this gives a way of dealing with these objects in any ring. But psi is rather complicated to define. And the nice thing about this quartic form is that it's a quartic form from A to R, not a 4 linear form from 4 copies of A to R. And so losing that would, so remember what I wanted to do. If we go back, I want to have some form to define these varieties, spheres and stuff. So I want one quartic form. And so that is why the actual sort of results that I will present to you that go somewhere, they require 6 to be invertible. But I just want to let you know that as of last year, there is a way, thanks to Garibaldi, Peterson, and Racine, to deal with these things over rings of any characteristic and without invertibility conditions. Now, so this was the reduced Freudenthal triple system. And so as you can imagine, a Freudenthal triple system just in general is a triple B, B, psi, where this is a projective module of rank 56. This is a bilinear form, and this is a 4 linear form. Such that if I extend scalars, I'll write it by tensoring the whole thing with S, this becomes like this, where, yeah, so maybe I should, no, let's keep it this way. So where S is FPPF over, faithfully flat over R. So both isomorphism of Freudenthal triple systems and scalar extension of Freudenthal triple systems are natural and can be defined in the sort of so-called obvious way. And if you do that, you require that after a nice enough extension of scalars, you get exactly this thing that I defined above. So in other words, we have to each Albert algebra, we have the reduced Brown algebra, and we have the reduced Freudenthal triple systems, and we can look at things that are locally isomorphic to these. So now, where do the groups come in? So these are the algebraic structures. Now we want to do some algebraic geometry to be able to get a geometric understanding of all these constructions. So for that, we need to involve the algebraic groups. And so first, we want the automorphism group of a reduced Brown algebra. What is that? And so we define these Brown algebras. The reduced Brown algebras are the ones that are sort of the most regular ones. What are their automorphism groups? And so indeed, we find that there is an injective morphism of affine group schemes iota from the isometry group of the cubic form N of the Albert algebra to the automorphism group of BA. So let me write this here, that N is the cubic form of the Albert algebra A. And this you always have. And then if 2 is invertible, then you get a split exact sequence. So you get a semi-direct product with the help of this embedding. So the automorphism group of BA is isomorphic to the isometry group of N, semi-direct product with the roots, the second roots of unity. So a couple of words about this proposition. First of all, what does it say? Well, it's a statement about affine group schemes. You can think of those as algebraic groups. They are algebraic groups indeed. And remember that the isometry group of the cubic form of an Albert algebra is simple of type E6. And so you can always embed this into the automorphism group. If 2 is invertible, then the automorphism group is isomorphic to this semi-direct product with U2. So in the generality, I'm stating this is in principle new. What was known? So this result is known over fields, even for any, for sort of type 1 Brown algebras, let's say. So for these reduced Brown algebras, this was known for a long time over fields, provided that the field didn't have characteristic 2 or 3. Going from fields to rings is just a use of formalism from descent theory and so on. So the non-trivial step was eliminating the requirement that 3 is invertible. And since Alberto El Duque is in the audience, I will talk a bit about characteristic 3. So what happens? Well, to prove this, if you assume that the characteristic is different from 3, people used some identity of Albert algebras that required characteristic different from 3. And so there are actually different identities of Albert algebras that do not require the characteristic to be different from 3, and you can use those instead. So by just looking for the right identity that only requires 2 to be invertible, you can establish this without requiring 3 to be invertible. And one remark in connection to this theorem is that using cohomology of groups, you can prove that, okay, the automorphism group of this reduced Brown algebra is a bit bigger than the isometry group of the Albert algebra, but actually two reduced Brown algebras BA and BA prime are isomorphic if and only if the Albert algebras A and A prime have isometric cubic norms. So in some sense, the Albert algebra captures all the relevant information of the Brown algebra, and we can, instead of bothering, so the problem is that this group is not connected because of the sum of direct product, but this remark tells us that, okay, we can forget about the Brown algebra itself and just look at the isometry group of the cubic form of the associated Albert algebra. So this brings groups of type E6 into the business. What about groups of type E7? So this was the automorphism group of the Brown algebra. Now we want to look at the invariance group of the Freudenthal triple system. So now A is again an Albert algebra. And I take this Freudenthal triple system associated to this. So this is BA, some B, and some psi. This is the associated Freudenthal triple system. So B is some bilinear form. Psi is a four-linear form that, if you assume 6 to be invertible, you can replace with a trilinear form or a quartic form, if you wish. So let's set G to be the automorphism group of this BA, B psi, sometimes called the invariance group. So then there is a result by Garibaldi, Peterson, Racine in 2022 that says that G is a simply connected group scheme of type E7. So that's how groups of type E7 come into the picture. Okay. So how do we relate? So now we got the isometry group of the norm of the Albert algebra, or more or less the automorphism group of the Brown algebra, that's E6. The automorphism group of the Freudenthal triple system, that's E7. But to do this whole yoga of torsors, I want to relate the E6 and E7. And so this is the sort of first result that required some serious work to get. And so let G1 be the set of all elements of G, so automorphisms of our Freudenthal triple system that fix the identity element. So remember, the underlying module of our Freudenthal triple system is a Brown algebra, and so it has a unity, and we require this to be fixed. For those of you who work in affine group schemes, I'm really defining here a subgroup scheme. So I should say that for any ring extension of R, we have this equation in that ring extension. But this is morally what this G1 is. And then G1 is isomorphic to the isometry group of the norm again. So why did this take work to do? Well, doing this under the assumption that 6 is invertible is not very difficult. So you can do this over, so let me, the proof idea is to do this over, you do this over Q, and then you use a result by Seshadri from 1977 on representations of, so if you have a representation of an algebraic group G and you over the integers and you tensor with Q and you look at fixed points, this is isomorphic to fixed points tensored by Q. This result is used frequently in Garibaldi, Peterson, and Racine, and using this, one can sort of get the results over the integers from the result over Q. And once you've got the result over the integers, you're done because you can extend to any ring. So this means that we have, so our conclusion is that we have G1 included in G here, and this is of type E6, and this is of type E7. And now we want to use this to understand E7 as a homogeneous space with structure group E6 and relate that to isotopes of Brown algebras. So isotopes. And henceforth, I will require 6 to be invertible. So if I'm over a field, then 2 and 3 shouldn't be the characteristic, but now I'm over a ring. So what is an isotopy between two Brown algebras? So if I have B a Brown algebra, it comes with a triple product x, y, z, which is defined in the following fashion, that x, y, z is xy involution z plus zy involution x minus zx involution y. And so an isotopy of Brown algebras B and B prime is a pair alpha beta of invertible linear maps from B to B prime, such that if I take phi of the triple product, and so phi, not phi, alpha, I get alpha of x, beta of y, alpha of z, triple product in B prime. So it's some generalization of isomorphism. And so one remark, as you would have expected if you have worked with isotopes of octonions or Jordan algebras, is that if B prime, if this is the case, if I have an isotopy from B to B prime, then B prime should be isomorphic to BU. And this is the principal isotope of B with respect to U in B. And in order not to burden this talk with details, I will just say that there is a concrete formula for this. I will not give the concrete formula. Because what you really can give a concrete formula for easily is this triple product. And so let's say, yeah, so. But then this U, another thing, that this U cannot be arbitrary. This U should have some regularity condition. And so I require U to be conjugate invertible. And so what does this mean? This means that V of U V should be the identity for some V in B. And what is this V U V? Well, V U V of W, this is the triple product U V W. So in other words, being isotopic to a given Brown algebra is being isomorphic to a principal isotope of it. Now I want to understand these principal isotopes using algebraic groups and vice versa. I see now in the chat that I missed a question of you2. Thank you for answering. Right, so now how do we relate all these things and make them come together? So from the above, now let's, well, okay, before stating the proposition, maybe I should ask if there are any questions or remarks so far. If the technicalities so far have been a bit strange, I hope now that they will somehow come together. So let's say BA B psi be a Freudenthal algebral system of this shape, and recall this defines a quartic form that I did not write down explicitly because it's just a technical formula, quartic form from BA to R. And so I set the sphere of this quartic form, abusing notation, to be just the set of all x in BA, such that the quartic form value of x is equal to 1. Okay. Then the group G, so this is the automorphism group of BA, B psi, acts on S of Q, and the stabilizer of the unity is the group G1. Of course, that's almost by definition. But so this gives a homogeneous space, a principal homogeneous space, a G1 torsor, defined by the following map. Pi, where pi of phi is simply phi of 1. And this is a G1 torsor with respect to the FPPF topology. What does this mean? This means that I have this fibration of this group G over this variety. But this map pi is sort of, it's not surjective. This torsor is not trivial. G is not just the product space of SQ with G1. So the fibers are twists of this group G1 that I wrote like that in my previous slide. So they're not, it doesn't trivialize, but after a faithfully flat extension, it will trivialize. So what do you use this torsor for? So using this torsor, one can twist the Brown algebra BA. So how does this work? So I take an element U in S of Q. And I write E for the set pi, the pre-image of U. So this lies in G. Then the twist, let's maybe write this as E sub U to keep track of the U. So the twist, yeah, this is the set EU times BA modulo some equivalence relation with new multiplication, addition, and scalar action defined by U. So for example, if I write an element here as phi x, the multiplication of phi x with psi, or say rho y, would be something like phi and then x dot phi inverse rho of y. So this looks technical, and it is. And the point is, this is something that one has for free whenever one has a torsor. One can use the torsor to twist whatever algebra one starts with. And through these complicated formulas, one gets an algebra that is not necessarily isomorphic to the original algebra, BA, Brown algebra, but becomes so after an extension of scalars that is faithfully flat. This is the machinery of algebraic geometry. Now, the result here is that this complicated twist EUBA is isomorphic to the principal isotope of BA with respect to U tilde. So this is the principal isotope. And U hat is the conjugate inverse of U. So there's a lot going in here. One has to prove that if an element has norm 1, then it is conjugate invertible, it has a conjugate inverse, and the twist is on the nose, the isotope. So this means that we have now an understanding of what this torsor, where we took G onto SQ. So morally, this G1 torsor parametrizes the isotopes. Why is this helpful to know? Well, first of all, this was a group of E7, and this is a group of type E6. So if you come from the algebra side, this gives you a concrete way of viewing the relation between groups of type E6 and type E7. But this is good news for us algebraists as well, because there are things you can say that come for free from this torsor machinery. So I shouldn't say corollary, but let me end with this proposition. So over fields, Brown algebras that are isotopes are always isomorphic. If you have two Brown algebras and one is an isotope of another, over fields, they are always isomorphic. Is that still true over rings? And the answer is no. So there is a smooth ring over the complex numbers, so nice enough ring over the complex numbers, such that the split Brown algebra, the one obtained from the split algebra, over this ring R, has non-isomorphic isotopes. And this is something that would be very hard to try to conclude without just sort of concretely. We need for that these torsors and trying to understand when these torsors are non-trivial, so we can use them to twist our algebra, and then the twists will be exactly the isotopes. Once you prove that, then you know that this means that isotopes will be non-isomorphic. And this is analogous to what was done by Philippe Gilles and myself for octonion algebras and what I did for Albert algebras. So now we've taken this one step forward to E6 and E7. And I think I am just on time to stop here. So I'll do that. Thank you for your attention.
Thank you very much. Are there any questions?
I think Alberto has a hand.
Ask a question. Yes.
Yes.
Hi, Seidon. It's wonderful talk. In this last part of the isotopes, you assume that 6 is invertible, right?
Yes.
Is there any chance that this can be extended to general rings, or do you have any idea how to proceed?
Yeah, so that's of course a very valid question that I tried and sort of didn't find a satisfying answer. So here is the problem. The problem is that when 6 is invertible, then you have this quartic form Q. So you can look at Q of X and it means something. If 6 is not invertible, or just in general, instead of this quartic form, you have this form psi. So that is a 4-linear form. And if you take psi x, 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 then everything will die because you'll get a factor 12 coming out. But you can take x, x, y, and then you will get something. And so my idea was that instead of looking at just elements x with norm 1, you look at pairs x, y, satisfying some conditions. So ideally, maybe you want to look at a pair. So instead of 1, 1, 0, 0, you replace this by the pair, this thing, and do something, and look at the variety of reasonable such pairs. And there is a notion of singular pairs that Garibaldi has done over fields that might be helpful here. So that is one idea, but I didn't pursue this very far. So I don't know if this actually works, but somehow it becomes a bit more technical and it's not very satisfactory, I would say, because you have these pairs.
Okay, yeah, and if I may ask another question, you mentioned at a certain point just that in this general setting, the automorphisms of the reduced Freudenthal triple system is a group scheme of type E7, right?
Yes.
Are all groups of type E7, all simply connected groups of type E7 automorphisms of Freudenthal triple systems? Or?
Oh, yeah, this was Garibaldi's result. I think it's not, it's all, you need an adjective. And so first of all, any Freudenthal triple system, even if it's not reduced by descent, has an automorphism group of type E7. Mm-hmm. And all groups of type E7 that are, I think, something like strictly inner forms,
I see.
Such thing, they can be obtained. The precise description is in Garibaldi, Peterson, Racine on archive, but I think strictly inner is the strongly inner is the right condition.
Okay, thank you very much, and thank you for this beautiful talk.
Thank you very much. Thanks for coming.
Thank you for the question. Are there any other questions? Well, if not, let's thank the speaker again, and I think we can stop recording.